This Week in Science and Education is presented in association with the Science Coordinators and Consultants Association of Ontario. Visit their website at sccao.ca.
This Week in Science and Education is brought to you in part by the University of Western Ontario, www.uwo.ca. We thank them for their support. This Week in Science and Education is also brought to you by Laurentian University. Check out Laurentian at laurentian.ca. We thank them for their support.
Hey everybody, it's time for This Week in Science and Education. The show talks all about things science-related, education, and all that kind of jazz. Lots of fun. We have a great show today. This is episode 57. We're broadcasting live from the University of Toronto, and joining me as always, my good friends Colin, Jagoe, and Dr. Thomas Merritt. Hi guys.
Hey.
Hey.
Missed you guys. Thanks for pitching in the last 2 or 3 weeks while I've been off in Spain, having a good time. Thought about you while I was sipping Mai Tais and margaritas.
Yes, you sure
how
did.
How did everything go?
It wasn't the same without you.
Next time we'll come with you.
We got to get our story straight.
Yeah. I'm hearing one positive, one negative. That's good.
Pretty sure they've got science people in Spain that we can go and interview next time, Kevin. Just saying.
I think that's a good move. We'll set it up. Hey guys, we got an interesting topic today. This is episode 57. Did a meteorite help form life on Earth? And joining us is Greg Slater from McMaster University. Hi Greg, how are you?
Good, how are you guys?
Well, I think we're doing great. You and I first met over the summertime. We did a little interview at Mac, and I can't remember if this was one of the topics that we discussed at that time, but I'm really glad that we're going to be talking about it now because it's a fascinating idea, and as I understand it, we've been hit with some meteorites that have perhaps had some compounds or some materials that are in the meteorites that potentially have helped spark life on Earth millions of years ago. Have I got the understanding of that pretty much correct?
Yeah, I mean, kind of what we've got is that we are constantly being hit by meteorites of varying sizes and varying compositions, and many of them do carry organic compounds, and we assume that's happening now and was happening in the past. So Earth has constantly had an influx of organic molecules coming to it via meteorites.
So are we thinking then, Greg, and maybe this is an unfair question, but are we thinking that life would not have formed on Earth without some of these organic compounds from out there in the solar system?
I don't know that we could say go as far as that. We know that we needed organic compounds to start life. Obviously, life is built from organics, and so we need to build those molecules that began life using organic compounds. So we had to get them from somewhere. They would have potentially been some that were accreted when Earth was actually forming into a planet in the accretionary disk around the sun. But a lot of those might have gotten broken down or burnt up due to the high temperatures. Earth originally would have been pretty hot, and so a lot of that might have been broken down. And so you might imagine that we needed an influx of organics to come after Earth had kind of condensed into its rocky form.
So, Greg, are you a geologist, or what is actually your field of study, your expertise?
Yeah, my PhD is in geology. My undergraduate was in chemistry. So, I guess depending which one of those you prefer to pay attention to, I am one or the other, or I'm a geochemist, which is a combination of the two.
So, Colin, I'm thinking we need to head over to Mac there and maybe take a look at this meteorite if Greg's got it in his lab.
I like
That's
it.
Fascinating.
Yeah, pick it up and twirl it around your fingers. That would be awesome.
I want to get maybe just a bit of a definition out of you. Like the word organic has a lot of different connotations depending on who's saying it and for whatever reason. Can you talk about what organic compounds means in terms of the meteorite and in terms of life? Because if you think about organic chemistry, well, it's things with carbon. Well, that's a lot of things. Or organic in like a farming industry has a different connotation. So I'm just thinking about a high school kid. Can you identify what organic means in your definition in terms of these meteorite compounds?
Yeah, sure. So, I mean, organic in terms of chemistry really is referring to reduced carbon compounds, which is to say all the organic things that make up biology and biological systems. Most of the organics on Earth, the vast majority, are produced during photosynthesis. So it's carbon that was fixed from the atmosphere and produced into organic matter by plants, and then we all utilize the energy stored there for our operations. So one of the big questions that comes up then is, that's all great for us. We have plants and bacteria doing that right now, but at the start of life, obviously that wasn't happening, so you had to get organic compounds. But that is certainly very different than the organic farming definition or some of those words that get thrown around in the media. Frequently the media uses words to try and make things sound better. Organics are certainly necessary for life. All the food out there is organic, though.
Yeah,
there's very little inorganic food on the market. We'll start with question 1. How complex are the molecules? How simple are the molecules? How complex are the molecules? And then question B is, why do you think they're not from a terrestrial origin?
All right, so in terms of complexity, there's a fairly big range of types of organic molecules there. There's big kind of insoluble organic matter, which are carbon compounds that don't dissolve in the types of solvents that we would analyze things on Earth or on meteorites with. So those can be somewhat complex. The other molecules there tend to be smaller, but they are quite complex. So we have amino acids, we have carboxylic acids, which was the main part of the study I was involved in, and that was so things like acetic acid. So vinegar is present on the meteorite, and much larger forms of that than just vinegar. Other compounds you might find are polycyclic aromatic hydrocarbons. So if you've heard about them, they're PAHs, they're combustion products. And I actually didn't know this until we started this work. They're everywhere in space. There's a large number of organic compounds that come out of stars as the processes there happen and get scattered about throughout space. And a lot of them get stuck to particles like they do on Earth. And so they stick to meteorites or to planets or that kind of thing.
So it's not evidence that Picard has been through if you find combustion products in space.
No, not at all. That was quite interesting. So many people like to think about the origin of life. They like to talk about PAH world as that the first. Not everybody agrees with this theory by any means, but some people put forward that the first organic molecules that could have templated life could have been these PAHs, or polycyclic aromatic hydrocarbons. One of the arguments for that is there's lots of them in space, so we can certainly have them delivered to Earth.
Right. Okay, so, and then B is, why are these molecules not terrestrial?
Right, so that's obviously a big problem. Most meteorites, there's a big issue with looking at whether the things you see there are from the actual meteorite traveling through space that's arrived to Earth, or, what happened to it once it arrived here. I mean, you imagine a meteorite that fell on a golf course, which happened not too far from here a while ago. It landed in the grass and in all the fertilizers that they utilize and all the plants and microbes and everything that's there gets on the meteorite.
Yeah.
And it becomes very difficult to prove, if you find an organic, that it came with the meteorite and not from the ground it landed on. Same thing, many meteorites get picked up in Antarctica. They've many times sat there for hundreds of years or thousands of years. Things, have been happening to them. Water has been percolating over them. And so being certain a meteorite is pristine is a really big issue. The Tagish Lake meteorite, the one that we were reporting on, is really quite spectacular in that it fell in January in northern BC on a frozen lake in kind of the dead of winter. So it was very cold, and people saw it fall, and they actually put out a call on the radio and said, if you find anything that looks like a meteorite, A, don't touch it with your hands, please, because your hands will contaminate it.
Yeah.
Use a plastic bag, use something that you won't contact with, and B, keep it frozen. If you find it, put it in the bag in your freezer, because both of those factors are very, very big with Tagish Lake. It was collected within a week or so of when it fell onto this frozen lake, so it only sat outside for about a week. It was very cold temperatures, so things were not happening quickly. And also, the guy who collected it then transported it and put it in his freezer, and it has remained frozen essentially since it fell on Earth, which is fantastic because that, as we know, when you put your food in the freezer, everything lasts longer. Same with meteorites. We're going to keep the organic compounds that are there and preserve them from breaking down so we can go and look at them. So it's a fantastic specimen in terms of being having had a history that shows us it's not contaminated.
So one of the things that I was really interested in reading your paper was that that's all well and good, but there's nothing that you've told me that couldn't possibly be wrong, and you wouldn't know that, right? So, maybe the guy didn't keep it frozen as well as he thought, or maybe he was, sort of fussing with his fingers. But, I mean, so I'm looking at figure, scroll, 3. So you actually were able to look at the chemistry and get a good idea from the chemistry itself that what you're looking at is extraterrestrial. I think this would be something fun for teachers to be able to say to the kids, look, this is a chemical clue that what you're looking at is not from here. Because if it was from here, you'd find X, and instead we found B. So what was B?
Okay, well, I don't remember exactly which figure that one is off the top of my head. But I think one of the biggest things we were able to look at was doing what's called stable isotope or isotope analysis of the molecules that were on the meteorite. And so this is something that myself and others specialize in. And what we can do is we look at different forms of an element. So the elements in the periodic table are all there, and they all have a given molecular or atomic mass that we talk about. But in fact, for most elements, there's more than one mass of that element, and those are called isotopes. It's actually from the Greek. It means in the same place on the periodic table. So these things are things that have the same properties, but they differ in mass. So for myself and for that paper, we were looking at carbon isotopes. So most carbon is carbon-12, as everybody talks about, but about 1% of carbon is carbon-13. Just weighs one mass unit more, behaves pretty much the same way, except for mass-related things. So what we can do is we can use the ratio of 13 carbon to 12 carbon in something to look at where it comes from. Another one that's very important in the paper is hydrogen has deuterium, which is essentially hydrogen with an extra neutron. That's how this mass increases. And so it actually weighs mass 2 instead of mass 1. And that's that difference. We can look at that ratio of how many mass 2s there are to mass 1s or mass 13s to mass 12s and try and understand where something came from or what happened to it. So we were able to use that as a fingerprinting tool to look at the source of the compounds. Yeah. And I mean, this is widely used.
Yeah, and I thought that was awesome. I mean, it's such a nice way to be able to say that what you're looking at really is what you think it is, because you've got an external source that should be unbiased, that you're able to validate the assumptions that you've made. So I thought that was a lot of fun.
Gentlemen, this is a fascinating discussion, but we're going to have to take a quick 2-minute break here to thank our sponsors. We'll be right back in about 2 minutes. Thanks for sticking with us.
This Week in Science and Education is brought to you by Sheridan Institute of Technology and Advanced Learning. At Sheridan, students shine brighter. Check out sheridanc.on.ca.
And we're back. Our special guest today is Dr. Greg Slater from McMaster University. And, guys, I can't get my mind out of this, okay? You're a guy that's driving along the country road. You're in your pickup truck. In the morning, you hear a news report saying, hey, if you happen to see a meteorite, do this with it. And by the end of the day, this guy's got a meteorite in his freezer. And it's all, just picture that. He didn't think about that when he woke up that day. Anyways, I find that interesting. Colin, over to you, my friend, for some educational content, please.
Well, I actually have a couple of questions. I got thinking about some of the things that you talked about finding in there, things like amino acids, things like carboxylic acid and the PAHs. And you talked about maybe where some of the PAHs came from and that you find them in various places in space. My question is, what about amino acids? Are A, they found sort of all over in space, and then B, why might they form out there?
Okay, those are great questions. Many of the meteorites that we have analyzed do have amino acids present. And in fact, the way that we think they form is by a chemical reaction called a Strecker synthesis. And so this is where chemicals that are present on the surfaces of meteorites or in the conditions where the meteorites are forming are actually going through chemical reactions driven by either radioactive decay and heat or sometimes, in some cases, radiation from stars and other sources near them. And that will actually cause chemical reactions to happen that will form things as complex as amino acids. And we see quite a suite of amino acids present on many meteorites. The really interesting thing about the amino acids that we find on meteorites is that we can look at them chemically also to look as a tracer of whether they came from terrestrial sources or not. And that's by looking at their chirality or their handedness. So in complex carbon-containing molecules, things can be essentially mirror images of each other. So you can have something that's right-handed and something that's left-handed. It's the same molecule, it's just got a different handedness. And we can look at that from amino acids on meteorites and try and understand how that compares to life on Earth. And what it turns out is life on Earth uses only one-handed amino acids. It uses L amino acids. Pretty much all the amino acids that or the compounds that we're made of are this one-handedness. Right. Whereas on a meteorite, we actually see both. So we see what's called a racemic mixture. That is kind of a 50-50 split between these two. And that is one of the other evidences that these were not made by biology, but are in fact present on meteorites.
And then, wow, fascinating.
And by the way, that's figure 3.
Oh, that's figure 3. Well, and there's more to say about that, really.
Can I ask one question? So, devil's advocate, you found amino acids on meteorites, and that's evidence of life on other planets. Is there any reason that you would? I mean, this is amino acids are fairly complicated, and I've been reading. I mean, the idea of amino acids in meteorites has been around for a little while, but I can imagine somebody that's not familiar with basic chemistry saying that this is a function of life. That none of the molecules that you found, although they're fairly complex, actually require life to generate them. These can all be generated through relatively simple chemical reactions. That's right?
Yeah, absolutely. I would not say that any of the molecules we have found on the Tagish Lake meteorite or other meteorites are evidence that there was actually life involved in their production originally out in space. All of them have chemical reactions that could lead to their creation, and in fact, we either do those reactions in the labs on Earth. We'll do those in laboratory studies, and there's actually even other research that I've been involved in where we see actually that those types of reactions can happen in certain places on Earth, like very deep in the subsurface. We do work in the deep gold mines in Johannesburg, and also in northern Ontario in Timmins, and we find evidence of methane and hydrocarbons that look to be the result of water interacting with rock and actually producing organic reduced carbon.
Okay.
Wow.
Greg, what's the most interesting part of this or your research for you?
Well, I guess I think it's all very, very interesting. One of the coolest aspects when you're doing a project like the work on Tagish Lake is to realize that we're analyzing organic matter that we think and we believe was formed 4 billion years ago out in space, and then traveled around for all that time, and then ended up landing here and coming to my lab. So you're looking at these compounds that are this little picture of what might have been happening, a little window into a way to understand what was happening in space that long ago. And I think that's pretty amazing for this project.
And don't forget about the guy in the pickup truck that found it.
I didn't actually get to meet him, unfortunately.
Oh, you think? He's listening to the show. He's going to call you afterwards. Colin, last question goes to you today, my friend.
Okay, well, I'm sitting here. I got a lot of them, but I'll try and keep it just to the one. Then I'm thinking about this handedness thing again, and if through the chemistry, amino acids could form, say, right or left-handed, but then life preferentially uses this left-handed form, like you talked about. If these things arrive from space, would life have evolved to select just one of them, or is it an indication that life evolved separate from that? and that these are just arriving because they form in another way and get here anyway. Like, you know what I'm trying to say?
I think so, and it's a really good question as to why does life on Earth only use one, and how did that selection actually happen? And we don't really know the answer to that. It makes sense that in a system that is replicating itself, as life is, and that's one of the fundamental steps to have the origin of life, is to be able to self-replicate and replicate information. So it makes sense that if you start to make molecules that can do that, you're going to make them of the same handedness as the ones that you started with. So once the selection has started and you use one handedness, you're going to keep doing that. So that makes sense, but that's already, if you already have life, it makes sense that we keep using the same handedness. It is a very big question, how did that originally happen? So one of the things you observe on different components of Tagish Lake and in other meteorites is that the handedness is not exactly 50-50. There's actually excesses of 7% or 5% or 15% of one-handed or the other. And a big question is that enough to start this off? Is that little bit of a preference enough? We really don't know how to get the transition from kind of a 50-50 mix or something near thereabouts to 100%. And one might think that it was a 50-50 chance which one we ended up using. I mean, based on what we know, there's no reason that it should have been L instead of D.
Right.
We could have all been made out of the other one, and everything would work equally well.
Thomas, you probably have one last question. You're looking like you're jumping to ask one more question, but maybe you could just introduce the person letting all the fruit flies loose behind you there.
So, David, you want to wave? Oh. David is a student.
Students of French in. How about that?
David is a master's student who started in my lab in September, and he's been here, he said, since 6 a.m. sorting flies, so it's okay that he's back in here. All right, let me ask one quick question. The methane thing that you mentioned just in passing from the deep mine stuff, there was just an article in the New York Times where they're talking about looking for life on Mars, and one of the things they brought up was a study that was done, I think, whenever the rover was there, where they actually were able to find evidence for methane. And there was a certain camp saying that if you find methane, you found life. And apparently that's not true, right? And that didn't make it into the New York Times. So could you give me that argument again? You've got production of methane in abiotic fashion, is that correct? Without life.
Absolutely. So we have definitely done work in a number of environments, working with mines in the Canadian Shield and the South African Shield. These are old geologic environments. They're crystalline rock, and in some cases you will actually find places where you find small amounts, generally speaking, of methane or natural gas. These are not commercial deposits generally, like they're nothing like natural gas fields where we get energy to heat our homes and that kind of thing. But by looking at the isotope ratios of them, we can see evidence that they were actually produced by chemical reactions that were not involving biology, but in fact just water and rock. And we actually see these similar reactions happening near the mid-ocean ridges in the ocean. They've seen evidence of it in those environments as well.
All right, that's great. Thank you very much.
Hey, Greg, thanks very much for being on the show today. We really appreciate your time talking about this, your fascinating research and this article in particular. I know you've given us an awful lot to think about. Thanks very much.
Thanks a lot.
It was great to be here. Thanks for having me on.
Absolutely.
Our special guest today has been Dr. Greg Slater, Associate Professor from the School of Geography and Earth Sciences at McMaster University. And on behalf of Dr. Thomas Merritt and his graduate student at Laurentian University and Colin Jagoe from the Kawartha Pine Ridge District School Board, thanks everybody for tuning into This Week in Science and Education. We'll see you all again next week. Take care now.